Okay, let's practice doing some gravitational force calculations. Question number 1. How much would a 70.0 kilogram person weigh on Mercury? Now that doesn't seem like you have a whole lot of information, but let's just look at our question. We know that we have 70 kilograms. So our mass 1, doesn't matter which number you put, it could be mass 1 or mass 2, 70.0 kilograms. We know that our second object is the planet Mercury. And I will tell you that the mass of Mercury, M2, is 3.32 times 10 to the 23 kilograms. So here's our two object masses. Our distance is going to be the distance between the centers of those two objects. So the distance from the center of Mercury to the center of this person. And essentially that's just the radius of the planet Mercury. The height of a person is so tiny compared to the radius of a planet that it really doesn't make a difference. So our distance in this case, our D, 2.44 times 10 to the 6th meters. And we always know big G, our gravitational constant, you have to add that into every single calculation, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And when you plug all of these things into your formula, you're going to see that in finding force, the meter squared and the kilogram squared cancel out, and you're just left with newtons. So what are we looking for? We're looking for weight, which is the same as gravitational force. So we're looking for Fg. And we know that our equation for Fg is equal to big G times mass 1 times mass 2 divided by your distance squared. This distance squared is really, really important. It's going to make a huge difference in your final answer. So let's plug in what we know. So Fg is equal to, here's our big G, 6.67 times 10 to the negative 11, times our mass 1, which is 70.0, times our mass 2, which is 3.32 times 10 to the 23rd, divided by our distance squared. And normally I would tell you to put your units next to all of your numbers, but in this case it's okay to leave them out just if you are needing to save a little space. If you've got the room, go ahead and write your units in as well so you can get used to doing that. And when you plug all of this into your calculator, you should end up with Fg is equal to 260 newtons. If you set this up correctly and you plug it into your calculator and you don't get 260, we need to see what you might be doing wrong in terms of how you're plugging it into your calculator. Because with all of our exponents here, that can kind of mess you up just a little bit. So make sure you're setting it up correctly. And then, like I said, if you're not getting the same number, then we need to see what's going wrong there. This is another reason why you're going to be uploading a picture of your journal with all of your work shown so that I can see, is it just a matter of plugging it into the calculator, or are you actually setting up the problems incorrectly? Let's look at number 2. Peter has a mass of 90.0 kilograms and weighs 135 newtons while floating in space. How far above the surface of Earth is he? Now this is going to be really important. How far above the surface? So we're dealing with a little bit different than just the distance between two objects, but we'll get to that in a minute. First, let's look at what we know. We know mass 1, or the mass of Peter, 90 kilograms. I will tell you that the mass of the Earth, mass 2, 5.98 times 10 to the 24 kilograms. And we know that our force, our weight, is 135 newtons. We also know big G, 6.67 times 10 to the negative 11th. And we know that we're looking for a distance, okay? So D equals question mark. So we look at our equation for D, square root of big G times mass 1 times mass 2 divided by the force. The square root, again, is very important. It's going to make a big difference in your answer. So let's plug in what we know. 6.67 times 10 to the negative 11 times 90 times 5.98 times 10 to the 24th. All of that divided by 135. Do all of the underneath the square root sign first, and then take your square root. When you plug all of that in, you're going to get 1.63 times 10 to the 7th. But you're not actually done. 1.63 times 10 to the 7th meters is how far away from the center of Earth Peter is. But that's not what I'm asking. I want to know how far above the surface. So what we need to do is take this total distance and subtract the radius of Earth, which is 6.38 times 10 to the 6th meters. And that leaves us with 9.93 times 10 to the 6th meters. This is how far above the surface he is. This first number, how far away from the center of the Earth, but our final answer, how far above the surface is he? And not all of your distance problems are going to be this complicated. I just wanted to throw one in to make you think a little bit. Number 3. Captain Kirk beams down to a planet with a radius of 2.61 times 10 to the 7th meters and finds that his weight is 1,250 newtons. If Captain Kirk's mass is 80 kilograms, what is the mass of the planet? So we know mass 1, or the mass of Captain Kirk, 80 kilograms. We know that our force, our Fg, is 1,250 newtons. And we know that our distance, the distance between the centers of our objects, is 2.61 times 10 to the 7th meters. And once again, we know big G, 6.67 times 10 to the negative 11. And what we're looking for is our mass 2, our second mass. Now, in your notes, you've got an equation that says M1 is equal to whatever. Well, guess what? M2 is exactly the same formula, because it doesn't matter which one is mass 1 and which one is mass 2. You're going to plug them in the same way. So M2 is equal to force times distance squared divided by big G times mass 1. Now we're going to have to be careful when we plug this into our calculator, and I'll talk about that in just a moment. First, let's substitute what we know. 1,250 newtons times 2.61 times 10 to the 7th squared divided by our big G, 6.67 times 10 to the negative 11, and then divided by 80 kilograms. Now, what you guys always want to do, what students always want to do, is 1250 times this distance squared divided by big G, and then you want to put times 80. But don't do that because your calculator doesn't understand what you mean by that. Anything on the bottom of a fraction you're dividing by. So 1250 times 2.61 times 10 to the 7th squared divided by 6.67 times 10 to the negative 11 divided by 80. And when you plug that in correctly, it should give you an answer of 1.60, rounded, times 10 to the 26 kilograms. If you're getting an answer that's different than that, it probably is all coming down to how you're plugging it into your calculator. Either you're multiplying when you should divide, or perhaps you didn't square your distance, or sometimes it's leaving out big G. Okay? You're going to complete the last 3 problems on your own. Follow the same process that we just did. Feel free to watch the video again and see how to answer a particular problem. Again, make sure that you're showing all of your work in your journal so that just in case you do get the wrong number for your answer, I can see if you're setting it up correctly.